Hi everyone, hope everyone is okay and good evening. We are here for the Mr. X Physical Science free class. We are doing a grade 11 topic, but also it is examinable in grade 12. The topic is application to Newton's laws. It's a free class, so welcome and thank you for coming. But hey, there's more that's coming, and this is because I am embarking on a huge project in this particular year where I will be doing Zoom classes, online classes. And last year, when I was doing them, they were 100 rands for a lesson. A lesson is 2 hours, just like what we'll have here. But this year is a massive drop. It's going to be 50 rand per lesson. But the key is that you must pay for a minimum of 2 lessons at a time. I'm starting them on the 26th of February. And so if you consider the end of Feb, 26th of Feb, up to the end of March, it will give us a total of 5 lessons. 5 lessons for mathematics. I will do 5 lessons for physical sciences. I'll do 1 lesson per subject per week. So there's 5 weeks, that's 5 lessons, 250 per subject if you take 1 subject. But if you want to take all of them, it's going to be 500 rands, and we are going to be having a great time. So I do have a schedule as to what I'm going to be doing and which particular day and what topic I'm going to be doing. Today's topic is application to Newton's laws. That's just part 1, where there is the theory and some questions. But then next week, when I start off, I will start off with part 2. Actually, on the 29th of February, I'm doing part 2, and then there's also going to be part 3. These topics are huge, they're big, so you need to understand. And I want us to be very thorough when we learn to understand the concepts and to do our best in all circumstances. All right, having said that, I'm going to deactivate my video now, and then we get down to the business of the day. So if you would like to know more and get more details about this, do not hesitate to contact me. My number, and I'm going to put it on the group as well, is 073-974-8498. You can text me on WhatsApp, then I'll give you all the details that are necessary. All right, let's get down to business. All right, you can hear me, you can't see me no more, and we are doing the topic application to Newton's laws. I will send the notes that I already hear on this particular handout or this particular presentation that I'm doing now. I will send the notes to you guys so that at least you can be able to access what I have. But I'll also put this on my YouTube channel, and so we may learn. Here we go, application to Newton's laws. Now, to begin with, when you're dealing with application to Newton's laws, you first have to consider that any object for that matter, does not exist in isolation. So objects are always interacting with the world around them. So if you've got an object here and is on a horizontal surface, there is an interaction between the surface of the object or the surface itself of the horizontal place as well as the surface of the object. There's also other forces available. Force of gravity, if the object was moving, we'll speak about friction, so goes the story. The point is, objects do not exist in isolation. There are forces that are available. And I put a statement to say, whenever there is an interaction or whenever an interaction ceases or stops, then the objects no longer experience a force. And the forces only exist because of an interaction. So forces are available on objects. Objects, they interact with the world around them. If there's no longer any interaction, then the force does not exist between the objects. It is important, again, as we start this topic, to understand the effect of a force on objects. What can a force do? A force can increase or decrease the velocity of an object. So a force can change the velocity of an object. It is possible also that a force can change the direction of an object. It's also possible that a force can change the state of rest of an object. Let me explain that. Say an object is stationary, it's not moving, it is at rest. Those are the words that are used in physics. Stationary, not moving, at rest. Say an object is in a situation like that. If there is a force, it's possible that the state of rest can be altered. The force can actually cause the object to move. So that's why I said a force can change an object's state of rest. Also, a force available can actually cause an object to accelerate. Right at the bottom right corner of the screen, I put down different effects of a force. Here, there was a change in the shape of the object due to the force. Here, there is a change in the direction of this ball due to a force. Here, there is a particular stationary lawnmower which is now moving because of a force. On this side, the force is causing an increase in the speed. I need you to understand at any particular point what effects a force or forces have. Now, when you speak about forces in physics, you must speak about a force from the context of two positions. A force is a vector quantity. Forces are vectors. They belong to a group called vectors. Vectors are described by virtue of their magnitude and by virtue of their direction. Well, when you say magnitude, you are talking about the value, you are talking about the size, you're talking about the amount. So when you're describing a force, you must specify its value, which is magnitude, size, or amount, and its direction. The standard units of operation of forces or of measurement of forces are newtons. So the standard is actually newtons, as you can see there. Now, I did put a couple of examples and I'll just explain what I have. And I want to be very thorough. I'm going to be trying to be slow, but very efficient. And if you have any question, please let me know. Here's an arrow here. And why an arrow? Because in vector diagrams, an arrow is used to represent a force. So in vector diagrams, we use an arrow to represent a force. It is interesting to note that the direction of the arrow indicates the direction the force is acting. Here's the direction here. It looks like this 5 Newton force is acting to the right. Even this 10 Newton force is acting to the right. So the arrow's direction is the actual direction of the force. Secondly, the size of the arrow is reflective of the magnitude of the force. So how long that arrow is can tell you about the size or the magnitude, the amount, the quantity of that force. If you look at the examples that I put here, 5 Newton, it's shorter than the 10 Newton. 7 Newton is shorter than the 10 Newton. The 2 Newton is the shortest of them all. Hence, my statement, my notes read and say the size of the arrow is reflective of the magnitude of the force. So if the arrow is longer, then it means, therefore, the force is greater. Let me give you a bit of an idea. Check this out. Say, for an example, I have an object here, and on that object, there is an arrow this length, and I'll call this force 1, and there's another arrow this side, and I'll call this force 2. Notice that force 1 is acting to the right. That's the direction of force 1. Force 2 is acting to the left. By virtue of the size, F1 has a longer length. It means the magnitude or the size of force 1 is greater than the size of force 2. So I need us to understand this. The size represents the magnitude of that particular force, and the direction of the arrow also indicates the direction of the force. So please don't forget, a force is a vector. It means that when you're describing it, you must say what is the magnitude, what is the direction. 5 newtons to the right, 10 newtons, 10, that's the magnitude, newtons, the SI units, to the right direction, you are describing a vector. In physics, forces are grouped into 2 types, and we go on. This is just general, and I'm picking it up and building up a thought process. I know where I want to get you guys at. There are 2 groups that represent forces. The first one is the contact forces, and the second one is the non-contact forces. In essence, the contact forces are available when the 2 objects are physically in touch with each other. So they are physically touching each other. Object A right here, and then there is the surface right there, surface B. So the object A, the surface B, are in physical contact with one another. They belong to a group of forces known as contact forces. On my set of notes here, and your syllabus requires you to know these contact forces and to give examples of them. Applied force is an example, and I did put a diagram here. This is baseball. There is the ball itself. There is the bat, and then the baseball guy is applying a force on that particular ball. So there is contact between the bat and the ball. So it's a contact force, applied force. A resistance force, another example. Normal force, I'll go deeper on normal force later on. Frictional force, I'll also go deeper on that. Tension, elastic, so goes the story. Different examples of contact forces. On the flip side, non-contact forces exist when there is object A and there is object B, but they are at a certain distance away from each other. They are not physically in contact. They are non-contact objects, and the forces that act on them is or are non-contact forces. So there is a physical separation between object A and object B. And due to this particular separation, we find ourselves getting to a point to say the forces are non-contact. When I start my classes next week, part of the topics I'm going to do after I'm done with Newtons is a topic known as electrostatics. When I do that topic, I will speak about electrostatic forces as an example of a non-contact force. Don't miss that one. Great lesson, great learning. But more examples are available. Gravitational forces, non-contact. Magnetic forces, non-contact. Magnet A, magnet B. Between them, there is a typical kind of pull or push force, raised repulsion, and maybe even attraction, but the objects are not physically in contact with one another. All right, that's just basically the first parts. Let's keep going. We're learning, we're getting the content we need to understand. The normal force is a very important force in physics, and we need to be able to define it, to understand it, to be able to identify it in a typical question. When you speak about normal force, the word normal translated in physics, the word normal translated in physics means perpendicular to. That's what normal means. Perpendicular to. In other words, a normal force is a force that is perpendicular to the surfaces that are in contact. All right, listen to this. I put this on the side and I'm reading verbatim. The normal force is perpendicular to the surfaces in contact. Let me clarify. Let's do a simple example from what we see on the board here. So here is a typical object. This object is on a table. It's just like my laptop right now. It's on the table. Maybe your books as well on the table. Now, the object, your book, is in physical contact with the table. That's the first thing. So a normal force is an example of a contact force. Now, there is a force which is universally available, a force that always pulls objects towards the center of the earth. I think you have an idea what name that force is. The most popular force we have, Mr. Force of Gravity. The force of gravity, its intention is to pull that particular book through the table. Listen to my English. I'm explaining. We speak physics. The force of gravity, its intention is to pull that particular book that you are writing on through the table. That's what it wants to do. Then the normal force comes in and says, no, that's not going to happen. I'm going to exert a force that is opposite to the force due to gravity acting upward, while force due to gravity acts downwards. And so this normal force is what is keeping that particular book, my laptop, whatever you have on the table, so that it doesn't go through the table because of the pulling down of the force due to the force of gravity. So in essence, it is the surface of the table, follow my lead, and the surface of that particular book, laptop, or whatsoever. And so the normal force is a force that the surface of the table exerts on the book in an upward direction, and it is opposite to the force of gravity, ensuring that it keeps this particular book on that particular table. Now, it's very important to understand, and I'm saying this for now, though I will add more information later. Someone just asked, say, is the normal force equal to the force due to gravity? Under this scenario, in this case, yes. they are actually equal and opposite. If you were to just look at the size of the arrows, they actually decently look like the same length. They are opposite in direction. Maybe one is positive and the other is negative, but they are equal, and so they cancel each other out. I'll say these words as we go on. They cancel each other out. So this normal force is acting in pair with the force of gravity. So I want you to understand that. And so therefore, we need to understand that this is a normal force. And why do we say that? Because it acts perpendicular to the surfaces in contact. Here's the surface. Here is the object. The normal force is acting perpendicular to that particular surface. So there's my surface there, and then the normal force acts perpendicular to it. I want you to understand that the normal force always acts perpendicular. This is a very important point. The normal force always acts perpendicular regardless of whether the surface is horizontal or the surface is inclined. I'm going to say that, then I'm going to show it. Let me say that again. The normal force is always acting perpendicular to the surface, regardless of whether the surface is horizontal. So horizontal means the surface is like this, or the surface is inclined, it's at a certain angle, it is like this. So whether you are inclined, whether you are horizontal, the normal force will always act perpendicular. Now, also as well, before I move on to my next slide, I like this, and you will remember this when I do a question later on. Please follow this idea. This statement says, if there is no contact between the surfaces, there is no normal force. So if there is no contact, please notice that normal force is unavailable. Here's surface 1, surface 2, and there's a space in between them. So normal force will not be available. Here's my next slide, and here's the statement that I was giving. I was saying to you that the normal force, I'm reading this in bold, the normal force acts perpendicular to the surface irrespective of whether the surface is plane, the surface plane is horizontal or the surface plane is inclined. Normally, and I've already done this, we denote the symbol for normal force as just capital letter N or Fn. I prefer Fn, but it's really up to you. Either of them can be used interchangeably. Now, notice something. If you discuss this situation, the surface is horizontal, normal force perpendicular. The surface is inclined, normal force perpendicular. Even here, the surface is inclined, the normal force perpendicular. It's important as well, and I'm putting equations here, to understand that the normal force is equal to the force due to gravity on a horizontal surface. And so therefore, because it's equal to the force due to gravity, the formula for normal force on a horizontal surface, ngiyayiphinda lento, Chuck Norris, please listen to me. The normal force on a horizontal surface is equal to mg. Please remember this. On an incline, this diagram, on an incline, the formula for normal force is mg cos theta. I'm introducing the concept of cos theta. Later on, I'll show you how it comes alive. But for now, please notice that on a horizontal surface, the normal force formula is mg, but on an incline, the normal force formula is mg cos theta, where theta is the angle of inclination, where theta is the angle of inclination. I'm hoping people are writing this because it's very important, so that when you're given a question and you're asked for normal force, the first thing to ask is this object on a horizontal surface? If so, normal force mg. Is this object on an incline? If so, normal force mg cos theta. All right, let's move further on this one. So I'm done with normal force. Let's go to the interesting guy. His name is friction or frictional force. If there's questions or so, you can always raise your hand and I will attend to you. Let me try and see if there's a question. Please raise your hand. I will attend to you. Or you can just type, which is what some of you guys are doing. Someone says, say, the force of gravity Fg is facing, is it the negative? Meaning negative in mathematics. Does it remain negative in physics too? I'm not really understanding when you say is facing negative. Maybe try and lift up your hand and then I can unmute you and then can answer your question properly. Maybe something that you typed that I did not get. But while you're at it, frictional force is my guy. Listen to me. Now, frictional force, right? Frictional force is a force that acts opposite to the direction or intended direction of an object. All right, let me try and get a couple of questions here. Go ahead. I'm listening. I've unmuted you so you can ask.
Hi, sir.
Hi.
I wanted to confirm. You said Fg on an inclined plane is not equal to normal force.
I said Fn on an inclined plane is equal to mg cos theta.
Okay.
Then to answer what you said, to try and get context of what you said, I would say, and I'll show you this when I teach you the forces on an inclined plane, Fg, or rather, Fg perpendicular is the one that is actually equal to the normal force. Later on, when I teach you an incline, I will tell you that force of gravity on an incline is broken into two components, force of gravity perpendicular, which is the one equal to the normal force, and the other one known as force of gravity parallel, which I will deal with later on. So to get clarity on you, I am saying force of gravity perpendicular is the one that is equal to the normal force on an incline. On a horizontal surface, force normal is basically force of gravity, because on a horizontal surface, the force of gravity is not broken into its components. It's not acting at an angle. So it's just Fg on its own.
Okay, right. Thank you.
Anytime. All right, someone also has a hand. Go ahead. I am all ears.
Hi, sir. How are you?
I'm well.
So I would like to ask, is there a difference in the way you calculate normal force depending on the gradient of the slope of inclination?
All right. So is there a difference in the way you calculate the normal force depending on the gradient of inclination? I think by gradient, you're trying to say by the angle of inclination itself. Yes, the normal force will actually change as the angle changes, but I'm specifically talking about the angle of inclination, not on a horizontal surface. On an incline, when you change theta, you will also change normal force. Even when you change the mass of the object, you will also change the normal force. So basically, that's what you have. All right.
So
Okay, go ahead.
please, sorry, before you go on, so I think you misunderstood my question. My question was actually, does the way you calculate normal force change depending on like the way the slope is facing? If it's facing like left, as in the slope is decreasing, or if it's facing like on to the right, as in the slope is increasing, is there a difference in the way you calculate the normal force?
No. It's going to be the same thing. All right. So, okay, now I
Okay.
understand because, okay, you're talking about a slope like this and a slope like this.
Yes.
No. It's just
Yes,
the
sir.
same thing. Actually, the normal force is just dependent on this mass of an object, gravity, and the angle of inclination, not the direction of inclination, but the angle of inclination. All right. Okay. So let me go further on this one. Let me go to my typical frictional force. All right. So we keep going, fam, and trying to understand the best way possible from all of this. I'm taking this to frictional force. Let me start. The symbol for frictional force is small letter f, or you can write it as FF. By definition, frictional force opposes or is a force that opposes the motion of an object, and it acts parallel to the surface the object is in contact with. Let me say that again. Frictional force is defined as a force that acts opposite to the direction of motion of an object and is parallel to the surface. Let's do a practical thing. Here's an object. Here is a surface. Let's say the object is moving to the right. So I'll call this delta x the direction of movement of the object. By contrast, the force of friction, small letter f, or my preference, FF, is opposing the motion of an object. Here is Ukolani pulling an object. The frictional force is acting opposite to the direction of that particular object. The object is being pulled to the right. The frictional force is acting to the left. Here is Kolani's friend pushing this particular object, and it's moving to the right. But lo and behold, the force of friction is acting to the left. So again, I need this understood. The force of friction is a force that acts opposite to the direction of movement of an object. If the object was on an inclined surface and the object was moving upwards, then frictional force would act downwards. So the direction is upwards, frictional force acts downwards. If the object was moving downwards, best believe that frictional force will act the opposite direction, which is upwards. In essence, the force of friction is a force that is opposing the direction of motion of an object and is acting parallel to the surface the object is on. Your syllabus is insistent that you understand definitions. So I want you to get this right. Please listen to me very carefully because I want to go a bit deeper on this. Now, one of the biggest misconceptions is that if there's an applied force here, then the frictional force is always acting opposite the applied force. That's not true. That is not necessarily true. In the exam, remember my voice, do not be Chuck Norris. Frictional force does not by necessity oppose applied force. But by essence, frictional force is opposing the direction of displacement or motion of the object. Please don't make the mistake. It's not by necessity that friction is opposing applied force. No, 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 no. Friction is opposing the direction of displacement of the object. If the object is moving to the right, frictional force acts to the left. If the object is going up an incline, frictional force acts down that particular incline. Always, by essence, opposing the direction of the applied force direction of the motion of the object and acting parallel to the surface. Here's a colloquial basic definition of it. It is defined as the force that opposes the motion of the object and acts parallel to the surface the object is on. Understand as well that frictional force is a good example of a typical contact force. The surface and the object must be in contact for friction to take place. Let's talk about the coefficient of friction. Then I'm going to break some frictions as we go further. Listen to my story. Now, it's important to understand what is meant by the coefficient of friction. It is given by this Greek symbol. It's part of the alphabet of the Greek alphabet, all right? And it's pronounced as mu. So this is it. So Tina will call it U, but you know, it's mu, right? This mu is a symbol that stands for the coefficient of friction. Let me explain what that is. Follow my lead. Understand that different surfaces give rise to different frictions. I want you to understand that frictional force is also affected by the type of surface that you are on. Frictional force. So let's say this is a surface and it has got a lot of gravel, a lot of sand. I expect that the frictional force is greater here where there's a lot of sand, gravel, than in surface which is smooth, like the stoop. You know, stoop, ne? All right, like the stoop in your house, right? In America, what's a stoop? A Porsche. Okay, no, it's not the veranda. No, it's the Porsche, right? Like where, okay, the stoop. I think you know what I'm talking about. The stoop, right? So the stoop, which is shining, like the one that's at my grandmother's house, shining the stoop. And I want you to understand that the surface, the stoop, and the one where there is the gravel, where there is the typical sand, the stoop has a lower friction than the gravel surface. You go for ice skating. That surface has less friction as compared when you go to Durban, where there is sand on the beach, where there's a lot of friction right there. I want you to get the point. Different surfaces give different frictions. So the coefficient of friction is a value that tries to indicate how much frictional force would be available on a certain surface. And okay, sharp. Say routine, talk to us. Here's what I'm saying. Listen to me. The coefficient of friction is a value whose intention is to give a quantitative, whose intention is to give a quantitative analysis of the amount of frictional force that will be available on that surface. Okay, let's make it simpler and then go back to physics. The tube has a low value for the coefficient of friction. Why, say? Why? It's because the force required to move an object on the tube is less than the force required to move the same object on the gravel surface. Uthini Mr. X, man? Surface, object. Same object, different surface. This object here will experience less friction than this object. This object here will slide with less force, or less force is required to slide it as compared to this one here. In other words, the coefficient of frictions of these two particular objects, of these two objects at these two different surfaces are different. A high value of the coefficient of friction indicates that you require a greater force to move the object, and hence there is greater friction. And then on the flip side, a low value of the coefficient of friction indicates that you need less force to slide the object, hence the frictional force is less. And that's why in bold letters, I said a low value of coefficient of friction indicates that the force required for sliding to occur is less than the force required when the coefficient of friction is high. I also need you to understand that the value of the coefficient of friction can be close to 0 or greater than 1, but it's never negative. And it all depends on the type of materials available, the type of surfaces available. And I gave an example. I said ice on steel has a low coefficient of friction, while rubber on pavement, which is the tires, the car tires, has a comparatively high one. Now you need to be able to define what a coefficient of friction is, and also to get this point I'm going to bring across right now. In terms of definition, the red letters at the bottom of the screen, it says to me, the coefficient of friction is a ratio of the frictional force resisting the motion of two surfaces in contact, right, to the normal force pressing the two surfaces together, and it does not have any units because it's a ratio of forces. Right, let me explain, work with me, follow my lead. I got your back here. Look at this formula, I'll come back to the definition. According to the formula, the coefficient of friction is a ratio of the force of friction divided by the normal force. It explains the last statement, which says it does not have any units. I will say, why? So you're just saying that it's a number without units. Yes, why say? The formula says frictional force, which is measured in newtons, over normal force, which is also measured in newtons. Newtons cancel each other out. So it does not have any units. They love asking this question in the multiple choice, where they ask you, why is it that the coefficient of friction does not have any units? Your answer is that it's a ratio of forces. So the newtons, they cancel each other out. So basically, as a formula, the coefficient of friction is the force of friction divided by the normal force. Now I'm going to come back to this as we go along through the lesson, but I want you to understand for now that it is basically defined as the ratio of the frictional force to the normal force, and it does not have any units. And because it doesn't have any units, it's a ratio of forces. Basically, that's one and the same thing. Now, two things, then I go to my next slide. Follow my lead. I got a couple of notes to run through. This part as well as this part. Okay, listen to me very carefully. It's important to understand that there's two types of coefficient of frictions, two types. There's what is known as the static coefficient of friction, static. So static coefficient of friction, which is given by this symbol that you're looking at here, mu s, that is the static coefficient of friction. Then there's mu k, which is the kinetic or the sliding coefficient of friction. The static coefficient of friction is available or is applicable when objects are stationary. I'll go deeper on this. Then the kinetic or sliding coefficient of friction is available when the objects are in motion. So I need you to get this. There is a coefficient of static friction when objects are stationary. There's a coefficient of kinetic friction when objects are in motion. The word kinetic is a Greek word. It's not really an original English word. Kinetic, kinematics, it involves movement. It's all about the physics of things that can move. So therefore, the kinetic coefficient of friction mu k when objects are in motion and static when objects are stationary. Now, follow me for more. Let's go. Let's start with static friction. I'll use the example of this particular couch, or you call it a sofa, or whatever you want to call it. Let me start with that example. I want you to follow my line of thinking. Here is you, and what are you trying to do? I'm trying to push this particular couch. That's what I'm trying to do. In other words, I am trying to apply a force. What is the intention? The intention is to move this couch. All right, I hear you. To move. Let's say I apply a force and the couch does not move. What could that mean? It could mean that the applied force is small. Let me speak English first. It could mean that you put in a small amount of force that is not enough to actually move that particular sofa or couch. All right, say you spoke English. You said I couldn't move this sofa because my force is small. That's English, say. Can you please speak physics, say? I got your back, Ndwana. Physics. The applied force is intentional in moving the object to the right. However, all objects have got what is called static friction. All stationary objects have static frictions. The static friction is a force that is opposing the tendency of motion of that object. The static friction says, what do you want to do to me? When you say, I want to move you. The static friction says, I don't want to move. And so therefore, the reason why the object does not move is because the applied force that you have applied is matched by the static friction. It is a force whose intention is to ensure that the object remains unmoved, static, stationary, static friction. It is the stubborn nature of the object to moving. I don't want to move. In spite of your applied force, I will match your energy and I'm not moving. So the applied force is equal to the static force, hence the object is not moving. So the physics of non-movement is that the applied force is being equated to by the static friction. I'm not going anywhere. I'm not moving. Let me read something on my notes here. Catch your back, boy. Catch your back. The object does not move. Hayibo. Kanjani. Kanjani, bro. Why? It's because the applied force is equal in magnitude and opposite to the static friction. What do you want to do? I want to move. So the applied force says, I want to move you this way. Static friction says, I'm going to oppose you. I will equate you and no one is moved. Hence, the physics says the object is held by static friction. All right, I need to get some feedback here. Are you guys with me? You know, don't be too quiet. You guys with me? Okay. Right, so I'm okay. Please give me a heads up if you're okay, understanding and all. All right, so thank you so much. I appreciate that. All right, let me keep going. So then you say to yourself, Yazin, Yazin, I'm not moving, man. I'm not moving. Then you call your friend, Zogala Paul. Let's try and move this thing. You increase the applied force. Static says, don't worry, Mtwana. I'm a self-regulating force. I love this English phrase. Static force is a self-regulating force. It's its own boss. It says, what have you done? You've increased the applied force, ne? I'll also increase me. I'll always match you. This guy is stubborn. I'm not moving. I've applied the force, me and my friend. Nothing is moving. So it means the applied force has increased, but in response to the increase in the applied force, the static frictional force also increases. Hence, I said it's a self-regulating force. It keeps increasing as you increase the applied force. In other words, the object remains at rest until the force of static friction is overcome. Now, hold on to this. Hold on to this. Let me help you. Let me help you. Just like stubbornness in life, you can be stubborn, but one day stubbornness will meet greater stubbornness and fire will break out. Yeah, maybe one time you beat them, you're stubborn. Maybe the next time. But best believe, Ntwana, stubbornness will meet greater stubbornness and eventually hellfire will take place. In other words, when it comes to this situation, when then can we move? When is it possible that movement is guaranteed? Movement is guaranteed when the applied force has increased so much that it is greater than what is known as the maximum static friction. Welcome to school. So it means static friction, its stubbornness results or gets to a certain level. It reaches a maximum value. When the applied force becomes greater than the maximum static friction, then movement is guaranteed. So just before the object gives in and starts moving, I need you to understand that the maximum static friction is just there before the object starts to move. Movement is guaranteed when the applied force is now greater than the maximum stubbornness. Hellfire is taking place right now. Somebody has got to move. All right. Say, we hear you. So say, Utini, can you summarize that, Mr. X? I got your back. Movement of an object is only available when the applied force is greater than the maximum static friction. I also want you to understand that when we applied the forces before and there was no movement, it was because the applied force was equated by that static friction. We increased the applied force, the static friction increased until it got to a certain maximum value. And so by essence, by definition, by calculation, the maximum static frictional force is given as mu Sn, where n is your normal force. So in terms of the formula for static friction, we are having it as mu Sn. I've said to you guys in the beginning of the lesson that I'm going to upload this thing on YouTube. All right. The lesson will be available on YouTube. All my free lessons are available on YouTube. It's only the paid lessons, the one I'm going to do next week. Those ones I do not upload on YouTube. They're paid for. You need to attend. You need to pay. It has to come at a price. I'm giving you quality at cheap prices, which is something that you don't find almost anywhere. Quality at affordable prices. All right. I'm ready. Say Utini, I'm saying Fs max is mu s, coefficient of static friction, multiplied by the normal force. All right, I'm learning. I'm moving further. So please write down that formula as well. I'm hoping that you're taking some side notes in Yana, just to get things going and all that, and we go further. All right, let's go to kinetic friction. Maybe someone is still writing the formula. Let's go to kinetic frictional force. Let's get some proper interaction on that one as we go further. All right, I'm ready on that one. Okay, here's my story. I'm ready. Kinetic frictional force. Kinetic means I'm moving. So kinetic frictional force means there is particular movement there. So in the previous side, we had given the idea that once the applied force is greater than the maximum static friction, then movement is guaranteed. When the object is moving now, the type of friction that it has is known as kinetic friction. So the kinetic friction is that force that opposes the motion of an object relative to the surface. So static is when it's stationary. When it's moving, we speak about kinetic frictional force. The kinetic frictional force has this particular formula right there. Fk is mu k n. And I need you to be specific. On a horizontal surface, one of my first questions I'm going to do is this. On a horizontal surface, the Fk is mu k mg on a horizontal surface. The force of kinetic friction has this formula. On an incline, the kinetic frictional force on an inclined surface, the kinetic frictional force is given by this formula where theta is the angle of inclination. In physics, with all circumstances, your choice of the equation is always dependent on the information given and what you are asked. So whether you pick this one, the information should be it's on a horizontal surface. Whether you pick this one, the information should be it's on an incline. Where you are saying Fk is mu k, coefficient of kinetic friction, multiplied by the mass of the object, multiplied by the gravitational acceleration, whose value is 9.8 meters per second squared, cos theta, where theta is that angle of inclination. And so, top of it, as I move on to my next slide, I need you to understand that the magnitude, the value of the kinetic frictional force will depend on two things: the coefficient of kinetic friction as well as the normal force. I need to get this right. I saw a question as I was preparing these handouts that asked whether theta will affect that particular force of kinetic friction. I'll deal with it later on. But for now, I need you to get this right. The coefficient of kinetic friction is the one that affects the kinetic friction much as the normal force. The formulas as seen. Please do not forget that. Interestingly, let me give you something to run about, okay? As I do the summary of this, then go to my I think I've got 2 or 3 more things left. Then we can do some couple of questions. Keep hanging in there. I'm trying to make sure that I give you proper content, proper understanding, and then you can do the questions with me. I'll tell you this, fam. You cannot answer what you don't understand. And sometimes people are very quick to look for questions, and the questions will frustrate you because you don't understand the content. You have to give time to learn the content intimately, thoroughly, properly. Then you can only answer what you understand. This is not a novel. You're not memorizing. These are not lyrics. This is not a song. These are facts. This is physics. You must be able to engage your brain into this and see from the words the reality of these facts. So don't be so quick to run and look for questions, yet you do not understand the content. Get the content, Chuck Norris, then answer the question. When we mark your final exams, one thing that we notice is that students don't understand what they are writing. It's because students are quick to answer what they don't know. Not just that, you are quick to answer questions in your own way, where now you change the question to suit yourself. A question 80, calculate the force of kinetic friction. Wena uthi hayi ngiyanizwa bafethu, cabanga ukuthi nifuna static, mina ngizobhala static. Kanjani bro? They're saying kinetic. What are you doing for static, man? So you need to understand content. Then you can be able to answer questions. So I'm taking my precious time for the content. All right. Now that that shouting has stopped, let's go to facts to remember. What do I need to remember? What do I need to remember? I need to remember that friction opposes motion. I need to remember that friction depends on the texture of the surfaces, which is just your coefficient of friction. I need to remember that friction is dependent on normal force. In fact, friction is directly proportional to the normal force. And so the mu has no units. I'm just summarizing. And the higher the mu, the rougher the surface, the more the friction. I also need you to remember that friction does not depend on the area of contact. In other words, if this object is occupying from his space to that space, and then this object is occupying from this space to that space, the area, it doesn't affect friction. The friction available here will be the same available here. It is not affected by the area of contact. This is what affects friction. Texture of the surfaces, what type of surfaces you have, as well as the normal force. And with the normal force, frictional force is directly proportional to the normal force. All right, I'm happy, I'm good. Let's go to Newton's laws. Finally. Yo, kunini. We've been waiting for Mr. Newton. Where have you been? How Newton, my Newton? Talk to me. Somebody's got their hand up. I'm ready. Go ahead.
So I would like to ask a question. Since friction is directly proportional to the normal force, does that mean it's also directly proportional to the weight of the object?
So you're saying since friction is directly proportional to the normal force, then by contrast, it's directly proportional to the weight of the object? No.
Yes, sir.
Let me give you an idea where how you look at it. Okay, let me go back a bit. Right. The weight of the object is when you're dealing with a horizontal surface, and I say to you Fg, then Fn, and I said Fn is equal to Fg. But then that was on a horizontal. On an incline, I gave the idea, and I'm going to show it when I show you the free body diagrams. If this is your normal force, then this force, which is straight, is the force due to gravity perpendicular. See, this is gravity perpendicular, which is different from gravity itself. So therefore, it will not be correct to say because frictional force is directly proportional to the normal force, it's automatically directly proportional to the weight. Because the weight and friction are equal only if the surface is horizontal. But when the surface is inclined, we talk about force of gravity perpendicular, which incorporates the components of forces. Hence, force of gravity perpendicular is mg cos theta, while force of gravity is mg. So frictional force is just directly proportional to the normal force. It will then depend on what that normal force is, depending on the surface. To say that it's directly proportional to the force of gravity only would be to concentrate on the horizontal surface and to eliminate the incline where the normal force is equal to force of gravity perpendicular, which is a value different from force of gravity. So it's directly proportional to the normal force. Then we need to go back and say, what is that normal force? It is Fg on a horizontal. It is Fg perpendicular on an incline. All right, I'm hoping that's understood. I want to go further to my laws. Thank you for those questions, much appreciated. Newton has 3 laws. Newton's 3 laws of motion. Your syllabus requires you to state them and then to use them as well. Please understand that when stating the laws or when defining anything, it's either you get 2 marks or 0 marks. I need you to get this. They are very strict on definitions. They want you to know. So you can't say, I know a bit. Hey, sometimes I know. Hey, other times I don't know. No. Chuck Norris, you've got to know. Got to know properly. Here's Newton's first law. Newton's first law says an object will remain at rest or moving at uniform motion unless it is acted upon by a net or resultant force. All right, speak to us. Newton says this ball will continue at rest unless it is acted upon by an external force. So if we leave this ball here tonight and go somewhere, we'll come back tomorrow and find it at the same place unmoved, remaining in its position of rest unless it is acted upon by an external force. That's Newton. Newton then says also an object will continue moving at uniform motion 20 meters per second, 20 meters per second, 20 meters per second, 20 meters per second, unless it is acted upon by an external force. So Newton says, oh, you got to listen to this. Things will continue the way they are unless they are changed. You will continue not passing at school unless you change your attitude towards school. You will continue with 30%, 30%, 30% until you make a direct decision to change and get better marks. Things continue the way they are unless acted upon by an external force. As in, when I was doing my TikTok videos, I said this. I said, you will continue, and I was in class by then, I said, you will continue being single for the rest of your life unless you start posting pictures. That's what I said. Newton says, an object, I want you guys to understand this because these things are the things that make sense to you. An object will continue in a state of rest or uniform motion unless acted upon by an external force. And so that's how you state Newton's first law. I gave a couple of examples, hey? I said, okay, this is a car at a stoplight, okay? It means that this car will continue there unless the driver decides to move. This is a person doing ice skating. So this person will continue sliding nicely downwards unless it decides to change or is acted upon by an external force. A soccer ball at rest, roller coaster, a swinging pendulum, all those different scenarios at the end of the day. So an object will continue in a state of rest or uniform motion unless acted upon by an external force. And let me just bring an idea that resonates with the first law. Usually, sometimes this idea is spoken about interchangeably. Inertia. So all objects have inertia with them. It is a property of matter, a property of objects, by which an object will remain at rest or in uniform motion unless acted upon by an external force. In other words, I'm saying there's a certain level of stubbornness to objects. Either they want to remain stationary or they want to remain moving at the same uniform, constant velocity. It's just pretty much like humans. Humans are not the easiest creatures to change. We are creatures of habit. We want to remain at rest or want to remain with 20 meters per second. Don't trouble me. I just want 20 meters per second. 20 meters. So we'll continue at rest or 20 meters per second unless acted upon. And inertia is basically a quantitative analysis, which is very dependent on the mass of an object. Let me explain that. The larger the mass, the greater its stubbornness to move. The larger the mass, the greater its stubbornness to change when it's already moving. So inertia is basically that quantitative measure which is dependent on the mass of an object. So it's pretty much tied down to Newton's first law, but when asked in your questions, please write this one. An object continues in a state of rest or uniform, which is constant velocity, unless it is acted upon by an unbalanced, which is net or resultant force. All right, I'm ready for my next one, Newton's second law. Newton's second law says, okay, now that an object is moving, there is a force that acts on it. In the beginning of my lesson, I gave the idea that when there is a force it can cause an object to move. I even said a force can cause an object to accelerate. So Newton's second law, which is the most popular of them all, Newton's second law, it gives us an idea that when there's a force that acts on the object will accelerate in the direction of the force. So here's an object here. There's a force acting on the object. Come in, Newton's second law. This force will cause the object to accelerate, and the object will accelerate in the same direction as the force. And the acceleration of that object is directly proportional to the force. There you are. So what it means is that the more the force, the more the acceleration. If you kick a ball with a greater force, it moves faster than if you kicked it with a lesser force. So Newton says when the force is acting on the object, it causes the object to accelerate in its direction, and the acceleration of the object is directly proportional to the force, but inversely proportional to the mass of the object. Inversely proportional to the mass of the object. In other words, more mass means less acceleration. So the greater the mass of the object, the less it accelerates when acted on by a force. I did try to give some examples here. Small mass leads to larger acceleration. So the smaller the mass, the greater the acceleration. That's why I said they are inversely proportional. Larger mass leads to smaller acceleration. Ultimately, Newton's second law is summarized by the equation that says the net force that acts on an object is equal to the mass of that object multiplied by the acceleration of that object. That's Newton's second law. It's the longest and the most important. So I want you to be able to get here, get this proper, and work with it. So it says again, when there is a force that acts on the object, it causes the object to accelerate, and the object will accelerate in the direction of that force. Its acceleration is directly proportional to the net force or the force, but inversely proportional to the mass of the object. More force, more acceleration. Less mass, more acceleration. So that's Newton's second law. Again, they need you to state it. In our calculations, we use Newton's second law more than any other law. It's the one with the formula. Then let's go to Newton's third law. Action, reaction. I think that's what your teachers tell you in class. Action, reaction, forces. Action, reaction, forces. Newton's third law. Newton's third law says that when two objects exert a force on each other, so object A, object B, the force that A exerts on B is the same as the force that B exerts on A. They are equal in magnitude, but they are opposite in direction. So when one body exerts a force on a second body, the second body exerts a force of equal magnitude in the opposite direction to the first body. It's the most It's the one that's easily understood, Newton's third law. Here are two ice skating dancers, and this lady is exerting a force on the guy B, and guy B is exerting the same equal force on the lady A, but the forces are opposite, though they are equal. Even when firing a gun, the recoil force on the gun is the reaction, then the action is the acceleration force of the bullet. Even when you are on a typical boat, when you jump off the boat, you apply a force on the boat and the boat applies a force on you. Even when you're wearing your heels on flick, it means that this pointer will apply a force on the ground and the ground will apply an equal but opposite force on that particular pointer or shoe. That's Newton's third law. So in essence, these are the laws and how you must state them. But Newton is a genius, Ntwana. Newton has everything that we need to know about the world. There is another law, a law by Newton, which is known as the universal law of gravitation. When I teach you the topic electrostatics, when I talk about small charges, positive charges, negative charges, I will come to a situation where I will speak to you about the formulas and they will look almost like this. It's interesting how science is interactive. Let's speak Newton's universal law of gravitation. Let me give you a background so you can understand. Objects with mass exert forces on each other. Any object, any two objects, three objects with masses, they exert forces on each other. Even me and you, when we're standing next to each other, in your family right now, there's people there, they are exerting a force on you. Both of you guys have masses. They're exerting forces on you. Now, I need you to understand that these forces that are existing between objects with masses are directly proportional to the product of the masses, but inversely proportional to the square of the distance between the object's centers. I repeat, follow me, follow me. This is the sun, and this is Earth. There is the center of the sun, there is the center of Earth. I need you to understand that the sun exerts a force on Earth and Earth exerts a force on the sun equal to each other, these forces, according to Newton's third law. But the forces that the sun exerts on the Earth and Earth exerts on the sun are directly dependent on the product of the mass of the sun and the mass of Earth, and inversely proportional to the square of the distance between their centers. I need you to get that. And the reason why, let me just explain further. Remember I said to you, Guti, in your family right now, whoever you're next to, blah, 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 they exert a force on you. The reason why that force is not significant, why you're not pulled anyway by the presence of someone close to you, is because your masses are very small. So the forces are very insignificant. So I need you to get this. The force that is existing between two objects with a large value of masses is directly proportional to the product of the masses, inversely proportional to the square of the distance between their centers. And what I am saying is actually Newton's law of universal gravitation. It states that each body in the universe attracts every other body with a force that is directly proportional to the product of the masses and inversely proportional to the square of the distance between their centers. Ultimately, this definition is given in a formula which is available in your formula sheet as F is equal to G, M1, M2, all this over R squared, where M1 is the mass of the object 1, M2 is the mass of the second object, and R squared is the distance between their centers. And I did put down what the letter G stands for. It's the universal gravitation constant or gravitational constant whose value is this. An important thing to note under this topic is that sometimes you can deal with Earth, so you need to know the radius of Earth. It's available on the formula sheet as well. I just put it there. Also, you need to know the mass of the Earth. I also put it there. So in essence, basically, when dealing with universal law of gravitation, you are saying the bigger the mass is directly proportional, the greater the force. You are saying the smaller the distance between them, also the greater the force. The greater the distance between them, the smaller that force. Please keep that in mind as we go on this one here. All right, so here's what I was trying to explain by saying the bigger the what, the bigger the what. The bigger the what, the smaller the what. All right? And so I did put a couple of scenarios just to help you. All right, so you've got the mass here. Okay, let me use a different color pen. Got the mass M here, the mass M, the distance D, the force will be F. If you double this mass, you double the force. The distance is still D. If you double this mass and also double that mass 2M, 2M, the force is 4F, the distance is still D. If you make this 3 times as much and this one still M, that's 3F. So that's the effect of the mass. Changing the mass changes the force directly so. So you increase mass, you increase force. Look at the distance, which is more interesting. The effect of distance. So to begin with, mass, the distance is still D, the force is F. Let's change the distance. Let's make it twice as much. Then it means that the force becomes a quarter. Let me show you. F is inversely proportional to R squared. So if you make R twice as much, maths, it means it's 1 over 4 R squared. So your force is now a quarter less. So increasing the distance between objects decreases the force. So if you increase the distance by a factor of 2, then the force is decreased by a factor of 4 because you raise that 2D, 2 squared. So it's 2 squared, which is 4. So it's a quarter force because you must remember that the greater the distance, the less the force. Look at this. If you have the distance, make the distance smaller, you make the force bigger 4 times as much. And so in this case, again, you're simply alluding to the fact that the smaller the distance, the greater the force available. So these are the effects of mass and the effects of distance. And I know that on part 2 of this topic, I'll be going crazy while showing you the different scenarios. All right, let me move further quickly because I really want to do some questions. There's still some more information, but it's not as hectic as before. We are now slowly gravitating to doing questions. Now, here's one thing that's very important. I actually took this graph from a past exam paper so that I can show you the effect of acceleration due to gravity on Earth. So the acceleration due to gravity on Earth is actually measured as G, universal gravitational constant, mass of Earth over the radius squared of Earth. I want you to remember this. Now, you don't need to know how you get to the formula. You need to know how to use the formula, which is what one of you guys was saying. My problem is what formula to use. So when you're looking for the gravitational acceleration, is dependent on the mass of the object, is independent of the mass of the object, but dependent on the mass of the Earth or the planet that you're at. So it's not just on Earth. If this was on Mars, I would say G on Mars is mass of Mars and the radius of Mars. This just shows you that you can use this formula anyway. So the gravitational acceleration, we'll use this in questions, is equal to G, mass of that planet, over the radius squared of that planet. It's interesting to notice that the gravitational acceleration is actually directly proportional to the mass over r squared. That's what this straight line is showing you. That the relationship between G and m over r squared is directly proportional, as shown by this. It's a 2019 question where I took this from. And on my part 2, I'm going to do this question explaining everything as you would see it. All right, more things. I think 2 more things we should be done. Tension. All right, part of the forces that are available in this topic is tensional force. So it's a force that is a pulling force. And when you define it, it is a force transmitted through a cable, a rope, a string, or a wire when it is pulled by forces acting from opposite ends. Let's use this example here. Maybe these guys are doing a bit of some tug of war. So there will be tension on this particular rope. This guy is trying to pull this way. This one is trying to pull that way. So they are opposing forces on opposite ends. So tension is available. And so it's an example of a contact force because there must be a contact between the guy and the rope, or the guys and the rope, and there must be opposite forces, so tension is available. When I do a question or questions, you'll be able to see most of this thing. Let me see what else I have. This I wanted. All right. Let me see what else I have after this. Oh, lovely. Right, finally. Oh, finally. We're here. Components of a force. My first question will utilize what I'm teaching now. This part of the video is also available on my TikTok page. I actually explained this in detail, but let me give you an idea. Now, this is object A, whose mass is 2 kg. Object A is on a horizontal surface. That's where object A is, on a horizontal surface. And there is a force acting at an angle of 20 degrees. In other words, the force F is an inclined force. Please don't make a mistake. What is inclined is the force, not the surface. The surface is horizontal. The force is the one that is inclined. So when forces are acting at a certain angle, you have to resolve components. I think this is your first topic, vectors, resultant forces, and all that. Resolving of components of a force. So any force that acts at an angle can be resolved to two components. There is what is called Fx, which is the horizontal component of the force. There's what is called Fy, which is the vertical component of the force. This is taken from mathematics, because you see Fy, y-axis is vertical, Fx, x-axis is horizontal. So the Fy and the Fx. In terms of the Fy, the vertical component is given by the formula F sine theta. Let's say this was theta. Okay, I know it's A, but let me just use theta. F sine theta. So that vertical component of the force is actually F sine theta. This is coming from trigonometry. Let me show you some bit of some trig a bit so I can understand this maths. And by the way, those that don't know, I teach mathematics as well. So that's why my classes next week, Monday and Tuesday, is mathematics, grade 12 Monday, grade 11 Tuesday, Wednesday and Thursday is physics, Wednesday, grade 12 physics, and Thursday, grade 11 physics. Look at the maths, theta. This is F, and the angle here is 90. This side, or F, the one opposite 90 degrees, is the hypotenuse side. Then this side here, opposite theta, is the opposite side, which is Fy. And then this side here is the adjacent side, which is Fx. So if you say sine theta in maths using this diagram, is going to be opposite Fy over hypotenuse F. And if you want to make Fy the substitute of the formula, F sine theta is equal to Fy, which is what I wrote initially, to help you understand that the Fy vertical component is F sine theta. Similarly, cos, SOHCAHTOA, cos theta. Cos is adjacent over hypotenuse, so that's Fx over F. And so at the end of the day, your Fx is F cos theta. That's Fx. Please remember this, family. For the typical vertical component, then it's F sine theta. For the typical horizontal component, it's F cos theta. But, it will depend on the direction of the force. On my part 2 and 3, I'll show you what happens when you change the direction of the force. But for now, for the purposes of the example I'm going to give, this is basically what you need to know. All right, I'm good. I'm happy about that. So this one, who are you? Vertical component. And this one, who are you? Horizontal component. All right, let me show you something interesting as well. Then we can go to a question. Considering this object here, considering it, this is my Fy, and this direction would be my Fx. I think you guys must have done tail and head, tail and head. So I want you to notice something about the 2 kg. There is a force acting downward as always. It's a force due to gravity. There is another force acting upward. That is your normal force. But because of the fact that this F is acting at an angle, it gave birth to Fy, who is acting upward, just like the normal force. Now, usually, we have a situation like this. Usually we have this, where we usually say Fn will be equal to Fg, usually. But under this situation, notice that you've got two upward forces. Two upward forces. There is an Fy, I'm repeating, there is an Fn, and they're all acting upward, and the downward force is Fg. Therefore, it means the Fn plus the Fy are actually equal to the Fg under this scenario. Oh, please do not forget that. In a situation where there is a vertical component which is moving in the same direction as that typical normal force, then the two upward forces when added will equate the downward force gravity. Like I had said, usually you've got a situation like this, whereby you'd have your normal force just on its own upwards and your force of gravity, and you would quickly equate Fn to Fg. But whenever there is an applied force which is acting at an incline, you give birth to a new guy in the same direction as normal force in this scenario, which is Fy. Therefore, the Fn, the Fy, both being upward, are going to equate to the Fg. Perfect. All right. I'm hoping people get this because I'm going to use this now in an exam question. Past exam papers. Here's my mantra when it comes to school. The more you do, the more you know. Once you learn the content, run to past exam papers. Once you learn the content, run to past exam papers. Somebody wants me to repeat something. I'm not so sure what you would want me to repeat right there. So maybe just lift up your hand and just ask me what you probably would like me to reiterate on. All right, so because I've said a lot of things, so I really don't know what really you would want. But it's an interactive lesson as always. I really want you guys to be able to ask me, interact with me, learn from the comfort and the convenience of your home, really learning decent things and understanding. All right, go ahead. I'm listening.
Can you hear me, sir?
Yes, I can. Yes, I can. Go ahead. Yeah, I think the network could be a problem. Maybe you could type it right there. Okay. Right. You can also ask, yes, you can ask at any particular point. Let me try and unmute you. All right. Just make sure that when you ask a question, you are really in a quiet environment. It makes it easier even when others are watching on YouTube. Go ahead. I'm listening. I've unmuted you. Please go ahead.
Okay, sir.
Yes.
Sir? Yes, you can you hear me, sir?
Yes.
Yes, sir. So in a situation like this, you said that the force Y must be equal to the force must be equal to Fn. If it's a situation like this.
Okay, no, that's not what I said. I said in a
Okay.
situation like this, the force Y is acting in the same direction as the Fn. That's what I said.
Okay.
And the force Y plus the force Y, this one, plus the force N should be equal to the force of gravity. So this is two upward forces, will balance the downward force. So in other words, I said Fn plus Fy is Fg. That's what I said.
Oh, okay, sir.
All right, perfect. Thank you so much. Somebody says, please repeat about acceleration due to gravity. I think that's the thing where I said G is G. Then I said mass of whatever planet you have over the radius of that. So this is just another way of calculating the gravitational acceleration of the acceleration due to gravity, rather, of an object by understanding that it's equal to G, the universal gravitational constant, m, the mass of the object, divided by the distance between their centers. I'll show you via a question. Maybe it becomes a bit easier when you read a certain question. All right, so let me just quickly go to my questions. There we are. So where am I? Past exam papers. Here's my first one. Maybe write down the title. I always want people to know where they take these questions from. I will send this document so you don't need to write the whole question. We'll read it together. Says 2018, November, paper 1, question 3, and it reads as follows. A box with a mass of 45 kilograms is pulled with a force of 90 newtons at an angle of 50 degrees to the horizontal. The box moves capital letters at constant velocity. Let's just stop there just a bit. When you say an object is moving at constant velocity, it means that the acceleration of the object is 0 meters per second squared. This is because when you're defining acceleration, you define acceleration as the rate of change of velocity. So if something is constant, it's unchanging. That means the velocity change is 0. So once there's no change in velocity, the acceleration is 0. So I want you to note that constant velocity means the acceleration of the object is 0. But here's what it means further. Newton's second law told us that F net is mass times acceleration. Therefore, if the acceleration is 0 at constant velocity, it follows that the net force is also 0. So what am I learning? When an object moves at constant velocity, number 1, its acceleration is 0 meters per second squared. Number 2, its ultimate net force is also 0. So that's my scenario. And the questions follow like this. Define the term kinetic frictional force. I did give to you guys the definitions, but I took this from the memo as it is. That's why you can see there's 2 marks there. And I want you to write it as you see it. It is the force that opposes the motion of a moving object relative to a surface. That's how you define kinetic frictional force. I'm ready. I'm ready. Okay, we should have a next question here. We should have. So we've defined that. The next question, so the first couple of questions are just basic definitions. State Newton's first law of motion in words. I think to state it, I would say the one that I've just put across. A body will remain in a state of rest or motion at constant velocity unless a non-zero resultant or net force acts on it. That's basically the long and short of it. That's basically all right. So write down these definitions as you see them. Write down these definitions as you see them. Right, let's get down to where the calculations are. After writing the definitions, let's get down to where the calculations are. All right. Here is my next thing. Calculate, the question says, the magnitude of the horizontal component of the applied force. Calculate the magnitude. You can even take screenshots of this. I need you're using your phone or whatever. You can take screenshots of this. All right, so it's not hectic. Calculate the magnitude of the horizontal component of the applied force. So the applied force has 90 newtons acting at 50 degrees. And I remember when I tried to explain everything, I said in a situation like this, the horizontal component Fx is going to have the formula Fx is going to be F cos theta. The F is 90 times cos of the angle 50. So let me write it down. Cos 50 right there. In your calculator, you should get an answer like 57.85 newtons. So that is the magnitude of the horizontal component of the applied force. So it's a grade 11 paper, 2018 November. And by the way, this topic is done in grade 12. It's actually your second question in the final paper for matric. So you learn it now, you write it this year, you write it again next year. Ndona, don't miss this. Physics and maths, grade 11 is super important. People fail physical sciences, fail mathematics, not in grade 12, but in grade 11. You better fix yourself while you can. So that's 3.3. All right, I'm ready for the next one. The next one says, calculate the magnitude of the normal force, and it's 2 marks. Calculate the magnitude of the normal force, and it's 2 marks. Now, there's something interesting here. The normal force is an upward force. Then there's downward, which is the force of gravity. And then there's this Fy right there. Earlier on, I had said the normal force and the Fy, these two upward forces, are going to equate to the gravitational force. That's what I had said. I was saying the two upward forces. So somebody, if you said Fn is equal to Fg in this case, you'd be wrong because you are not considering the fact that there is Fy. You're not considering that. And that's a big problem right there. So you must consider the presence of the upward vertical component of F, which is Fy. And so the two upward forces added together equate to the force due to gravity. So I'm looking for normal force. That's what the question says. Calculate the magnitude of the normal force. It is going to be equal, we're doing math, Fg minus Fy. Fg is mass times gravity. Fy is the vertical. It's F sine theta. That's what I've been saying. It's F sine theta. And so now I put my numbers. The mass is 45 multiplied by G, 9.8, minus 90, then sine 50. In essence, your answer is going to be 372.06 newtons. That becomes your normal force, 4 marks. So you get a mark this way. Let me show you where the marks are. Get a mark for stating this part. You get a mark for writing this, a mark for that, and your 4th mark is your final answer. That's how you get this thing right. 372.06. That's 3.4. Please write this down. I'm trying to be slow but efficient. Somebody is saying, if I write the formula for normal force as for the formula as Fn plus Fy is equal to mg, will I be wrong? No, you'll be correct. Still fine. All right, I'm ready for my next one. I'm about to take this out. Going. Let's try the next question. I just want to see, right? Somebody says, say if I don't write the unit, will I get the mark? Yes, but no. Don't ever not write the units. They get very frustrated when you don't write the units because they'll be like, why? Why? What is it? 372 donkeys, monkeys, dogs. What is it? Give us a value. So make sure that you pull that through. The 9.8 is acceleration due to gravity. It's always 9.8. Look at the next question, 3.5. Calculate the coefficient of friction. Oh, yeah. The coefficient of friction. Here's my statement to remember all the time. Your choice of the equation always depends on the information given. Your choice of the equation always depends on the information that has been given. Now, follow my thinking. If I was to deal with the free body diagram of this object, I would agree that this is force due to gravity. I would agree. It's supposed to be just straight lines. Sorry about that. But I'm just trying to draw them this way. Fn is just straight lines, fam, please. And the arrows. And then this one will be Fx, which is the force on horizontal component. This one would be the force of friction. You can see it's shorter than Fx because the object is moving, showing that the object's Fx is causing the object to move. So it's got a greater magnitude of Fx. And then you've got this one here, which is basically Fy. I'm just doing a rough one, but on part 2, I'll show you more deeper ones as well. The vertical forces are equal and opposite all the time. The horizontal force is where the issue is because the object is moving horizontally. Now, when you deal with the net force, the word net means sum of all the forces. So I'm adding all these forces plus this, that, plus that. That's what net means. Now, we've established that Fn and Fy and Fg, eventually they cancel each other out, they give you 0. The object is moving to the right. That means the Fx is in the same direction as the displacement of the object. That's what it means, that Fx. So in terms of Fnet, it will be the Fx plus the force of friction. But note the following. The force of friction is acting opposite to the displacement of the object. And according to the rules of vectors, the force of friction should be negative because it's acting opposite to the displacement of the object. So in essence, the net force is actually fx minus fy. Okay, let me go back a bit on this. Gotta help you out. Please listen to this. I'm saying to you, the net force of the object is fx plus ff. This is because this upward and downward have cancelled each other out. So net means I'm adding plus. Net means I'm adding plus. But I'm saying, according to the rules then, we need to acknowledge that the fx is a positive force. Why, say? Why is the fx positive? Because it's moving in the same direction as the displacement of the object. Ff is opposing the displacement, so the force of friction is actually negative. Plus times minus, math is minus. So F net is Fx minus Fy. But F net at constant velocity is equal to 0. So 0 Fx minus Fy, it would mean Fy is equal to, sorry, not Fy, Ff. Why am I saying Fy now? It means Ff, sorry. It means Ff, eventually when I do the math, I'm going to take it to the other side. Ff will be equal to Fx. That's basically what it means. It means Ff is equal to Fx. Okay? But the question says, please find the coefficient of friction. Now, if Ff is equal to Fx, you see, in the memo, they don't show you this. That's why I don't like the memo, Mina. I prefer that I do things with you. The memo does shortcuts. Already from the question 3.3, we found out what Fx is. I think it was something to do with, I think it was 57.85. I think that was what F is. Fx rather is 57.85. That's Ff. But I'm not looking for Ff, Mina. I'm looking for the coefficient of friction. Your choice of the equation always depends on the information given. And so I acknowledge the following. Follow my lead. I acknowledge that Ff, according to the formula, is mu k n. Remember, I'm looking for the coefficient of friction. So in other words, mu k n is equal to 57, let me write it properly, 57.85. But I know normal force. I did calculate it in 3.4. So mu k multiplied by normal force 372.06 will be equal to 57.85. And if you divide both sides by 372.06, the mu k ends up as 0.16. Remember, it doesn't have units. It is a ratio of forces. It does not have units. It's a ratio of forces. That's how you get 3.5. So you needed to understand that, oh, okay, it means that in this case, then I have an Ff equal to an Fx because the net force is 0. Then I know what Fx is. Then I know the formula for Ff on a horizontal plane. And so it's mu kn. And from there on, you can simply find your typical mu k. So that's what you have right there. That's what you have. Okay, I think I'm okay with that. You can write this. And then I think this will be our last, we'll only do this question now. This is the only question we'll do. I've got so many, I had prepared so many. questions. Where did the 323,06 come from? 323. It's 372,06. Where did I write 323, Mina? It's the one that I got from 3.4. It's the normal force. Remember the formula says this mu kn, that's normal force, this 372,06. So that's where it comes from the previous answer. That's why it's important to really get the previous answers correct, because they come through. So somebody says, say if an object is moving at constant velocity, does it mean that fx is equal to fx is equal to ff? Not all the time, because sometimes you could have other forces available, like when there's tension and stuff, so it becomes a bit tricky. So that's why I really never want my students to memorize a situation, because the situations can come differently. We need to get the concept. The reason why fx is equal to ff is because these are the only two horizontal forces available, and the object is moving at constant velocity, and the vertical forces cancel each other out. So therefore, fx is ff. Then you can find the mu k. Okay. So it always depends on the scenario, right? So it always depends, because sometimes they can tell you that the object is moving, is not moving at constant velocity. They will tell you that there's acceleration. Now you need to get ma. So it's no longer f net is 0. So it always, this is why part 2, part 3 really deals in depth with all these different scenarios. I think there's a last question here. Oh yeah, there it is. Last question. It says, will the coefficient of kinetic friction change if the angle of the applied force is decreased? It says write yes or no and give a reason for the answer. Let me read that again. Will the coefficient of kinetic friction change if the angle of the applied force is decreased? So in other words, we move from 50 maybe to 40 to 30 or anything smaller. Will the coefficient of kinetic friction change? And the question says, right, yes or no, then you must give a reason for your answer. Okay, let me give an idea. The coefficient of kinetic friction is dependent on the nature of the surface or the type of material in contact. It's never affected by the angle of the applied force. And I say this because, Mina, I gave an example of a gravel situation, and I talked about a stoop, and I said the coefficient of kinetic friction is bigger here than here because the type of surface. What changed here, or what is supposed to change, is the applied force angle, not the surface. So because the surface remained the same, the coefficient of kinetic friction also remains the same. Hence, in our answer, we'll say no. You get a mark for saying no. Then you explain this way. I said no. Then you say the coefficient, no. Then you say the coefficient is dependent. The coefficient is dependent on the nature of the surfaces. The coefficient is dependent on the nature of the surfaces. Ah, beautiful. The coefficient is dependent on the nature of the surfaces. All right, perfect. Now, just so we may know, so the coefficient is dependent on the nature of the surfaces right there. All right. Now, having said that, fam, I would like to say thank you so much for coming to today's lesson. I think we actually even overshoot our time, but it's fine, it's good. At least I managed to teach the concept, and I'm hoping that you understood. In my culture, when someone does something nice for you, you say thank you. In my culture. And I think that is the African culture for all of us. We thank people that do things for us for good or from the goodness of their hearts, who could have been doing anything else, but they decided that let me spend this evening helping my students to understand. I really appreciate all of you. So I just want to give a reminder about the lessons that I'm going to be having, the big lessons, the Mr. X Zoom classes that are starting on the 26th of February, where I'm going to be dealing with all the things that you guys want me to deal with. Okay, no, there we are. All the things that you guys want me to deal with. And your typical topics, everything stationed. I've already put down for you guys what you need to know. So please do not hesitate to come through. Do not hesitate to learn more. So this is what I'm talking about here. The Mr. X classes that are going to take place 26th of February going onwards. And also it's important to understand that it's 50 Rand for a lesson. Imagine 2 hours, this kind of quality. You'll see next week I'm on fire. This kind of quality just for 50 Rand. But remember, you're supposed to pay for a minimum of 2 lessons. And also, family, I've got limited space. So please make your payments as soon as possible. Talk to your parents. Once I get to a maximum number, I'm going to close it down. You want to make sure that you use me to the best of your ability and gain a lot, because the more you do, the more you know. I already have a schedule for it. This is the schedule that you see there and the topics available from there on. Those who are not in my WhatsApp groups, who are not getting the information, I'm sending my number on the chat there, but I'm also going to say it, 073 974 8498. From my side as Utlolani or Mr. X, I want to thank you, and I'll stop the recording. Then we can have a bit of a chit chat, 2 minutes, 3 minutes, get to know each other. Then we vamoose. I'm stopping the recording.